Time to add an inner product to the vector space. Some standard inner products that are used extensively. So the inner product will be the angle brackets. For complex vectors, the conjugate transpose applied to V is the inner product. So given two complex vectors, U conjugate transpose applied to V. U conjugate transpose is a transformation going from C2 to C. So 3 plus I times the first column, 4 minus I times the second column, and I get a complex number. If I'm looking at real vectors, so just the special case of zero imaginary part, then U conjugate transpose is an R2 to R mapping. Now we can just say it's U transpose V. 3 times the first column, 4 times the second column. If U and V are functions, the integral of their product is an inner product. Here U and V are complex valued functions. In the special case of zero imaginary part, it's just the product of the functions. So if U is a polynomial and V is a polynomial on a restricted domain, say 0, 1, here's the inner product of U and V. That number. Abstracting these, we go to the definition, and there's 3 pieces. One is that the inner product with itself is always positive. 0 only when U is 0. Linear in each component. And conjugate symmetry. So if I flip the roles, I take the complex conjugate. Because of number 3, number 2 is usually phrased as linear in the first component, which we saw from our examples, because the first component is really a transformation, so it's linear. Now we can measure the size of a vector, is the square root of its inner product, and that's called the norm. It's a generalization of the absolute value. Just like with a number line, the first step is the most important. Vectors of length 1 will be called direction vectors. So a unit vector is just a vector scaled by its length. We call these direction vectors. The standard basis vectors all have length 1. To prove it, you just compute. Look at the square. Pull out the constants in each component. And the definition. Orthogonal projection is the big application of inner products. So 2 vectors, U, V. I'm going to scale V. Here it's extending. In general, it's just scaling. So a scale of V, so that when I add another vector to it to get back to U, I've formed a right angle. That's the geometry I want. So U is CV plus W. W then is U minus CV. And saying they're at right angles to each other, saying that they're at right angles to each other is saying that the inner product is 0. this to be consistent with dot products from physics. The dot products in R2 is an inner product. Orthogonal vectors are at 90 degrees to each other. That scaled vector v is the orthogonal projection of u onto v. Now let's find that scalar c. Inner product of v and w is 0. Swap in what w is. And use linearity. Break up sums. Pull out constants. And now I'll solve for c. This is rewritten often as divided by the length squared. So there's my scalar. A better way to think about this, I have two vectors, u and v, and I'll drop down a perpendicular. The length is the inner product of v with the u direction. So to get the vector, the orthogonal projection vector, I scale the unit vector by that length. And it's the same thing we just derived. This is the projection of v onto u. Well, if it's good for v onto u, it's good for u onto v. So we can do the exact same thing. I'll extend v into a line, drop down a perpendicular. That length is the inner product of u with the v direction. So to get the vector with that length, I scale the unit vector. Using linearity, that's the projection of u onto v. Abstract this now. I got a vector. If I take its span, I have a space, and I'm going to project onto that space. That's the projection of u onto v. A vector in, a vector out, linear transformation.